let's start. So, hi everyone. Good evening. My name is Rohit Kumar Singh, and I'm a PhD student at IIT Madras. So, this is my fifth year of PhD, hopefully the last year. And so, I am the teaching assistant for this course, Wave Optics. And this course is being taught by Professor Samudra Roy uh, of IIT Kharagpur over the NPTEL portal. So I'm assuming that you guys are following the lectures on the NPTEL website, and uh, so I will not be explaining everything. Like I'll recap some of the concepts, but you have to follow the lectures that are there on the NPTEL, and then you can come here and discuss your doubts and any question that you have. And in this live session that we'll have every Saturday, I'll try to solve some example problems which will help you do the tutorial assignment every week. So that is the plan and the goal of this live session. Okay. uh, so anyone has any question or anything to ask before we get started? Yeah, there is little bit of noise. Can you try to move to a better place? Hi, can you speak now?
I have to pay minutes and so anything about problem and ask
Sorry, sorry, I cannot hear you. There's too much noise. Maybe you can write in the chat if you have any question. Others can meanwhile ask if they have anything. Okay, okay, fine. So, yeah, if others are fine, let's begin. So, uh, first, like I said, I will just recap some of the concepts. And so, since this is the first live session, I will just start with very basics. So, as you know, this is wave optics. So, first of all, I would like to ask, what do you understand by the concept of wave? So, and one more thing. So, this is an interactive session. So, I would encourage everyone to interact and ask questions and answer questions if I ask. So, don't feel shy or hesitate. So, okay. So, the first thing I would like to know that how do you understand wave? Like, what is the understanding for you as a, I mean, for the wave, for the concept called wave? Anyone want to say anything? What do you understand by wave?
something that carry energy.
Uh, yeah, that is a very vague thing. So, Bhumika has written disturbance or vibration. Yeah, I mean, that is also not complete. All disturbances cannot be waves, right? But yeah, the disturbance word, I like it. Anyone else want to try? So I assume that all of you are in masters, or some of you are in undergrads student also. I mean, just to know what kind of understanding you have, so that I can adapt. Okay, so Aditya has written energy transfer. Wait, what? Energy transfer through disturbances. Yeah, that is more accurate. So or you can simply, yeah, energy, I mean, it is right that uh, every wave carries some energy, but yeah, simply you can say that propagation of disturbances, right? So if you make some disturbance in anywhere and it propagates to other place and time, then that propagation of disturbance is what is known as a wave. Okay, yeah, thank you. So yeah, this is the very basic idea. No, as someone mentioned, all waves carry energy, okay, and it has a fixed wavelength and frequency. Yeah. Aditi is writing inertia and elasticity is key factor. Yeah, but it depends on which kind of wave we are talking about. If you're talking about mechanical wave, then yeah, elasticity is there. But there are all kinds of wave, and we will just keep things generalized right now, and we will discuss them. So, okay, sorry. I'm Dr. Ashish Tiwari, not Aditi. Okay, Dr. Ashish Tiwari. Okay, thank you. So, yeah, as I mentioned, so all waves carry energy and they have a wavelength and frequency. Okay, so anyone would like to say what is a wavelength? How do you define wavelength? Everyone, everyone should know what is wavelength, right? Distance between two identical points on a wave. Yeah, that is fine. Distance between two crests. So Dr. Ashish Tiwari said difference between two crests. Yeah, this is also true, but yeah, I mean both are correct. But to be just more generalized, we can say that any 2 point separated by the wavelength will have same disturbance, or you know more formally displacement. Okay, so you know that if you throw a stone in the water, you will see these waves propagating, right? And the wavelength will be that distance at which any 2 point will have the same displacement. Okay, so here the displaced object is molecules of water. So you take a molecule of water and you see how it is getting displaced by the wave. And similarly for different types of waves, so like if you have a wave on a string, so suppose this you have a string, okay, and you are creating a wave by moving this point up and down. Okay, and so here the wavelength will be like, take this point and take this point, this will be your wavelength, right? Those have the same displacement in, so this is x direction, let's say this is g direction. Okay, Is it fine with everyone? This definition, or you have confusion? Okay, now, so this kind of wave, uh, thank you. So this kind of wave, how can we describe it mathematically? Like, so you can see here that this looks like a, mathematically this looks like a cos or sine function, right? So you know that, so we can write it simply like x is equal to cos of some, so this is z direction, so simply we can write it as cos, so some constant k, sorry, right? We can write, what you are looking at the screen, we can simply write it like this, right? This is just a cos function. But now this is not a wave right now, okay? This is a static function. Now what will happen is that as the time goes on, sorry, someone has raised hand. Sumit,
Yeah.
yeah, hi.
Hello. Am I audible now?
Yeah.
So I had a doubt regarding problem 4 of assignment.
Wait, we will go there. We'll go there. I would like to just get some basics clear. Then we will do the. I will solve some example problems, and then I will take any doubts or confusion that you have. Okay.
Okay.
Yeah. So sorry. So yeah, just wait. Okay. So now, as I was saying, so this is just a static function, right? Now, to get a wave, you have to look at this changes with time. So this is at time, say suppose t, then at time t plus some delta t, uh, this will have some change. So this wave will look like, so this, right? And so there will be a displacement. There will be a, yeah. And this displacement will be by distance. So if the velocity of the point on this string is v, then this distance will be v delta t, right? And so for a given time, for a given finite time t, uh, this whole wave will shift in the positive z direction, and how to write the write the function for a shifted how to write a shifted cos function. So this, it's just uh, j minus vt, right? Okay, so now this is your wave function basically. So this equation describes a wave, okay, propagating in the z direction, positive z direction with velocity v. And from here you can get everything. So also if you have a if this magnitude in the x direction is not unity but some a, then you will have to put a here, and then you can write it like this. So kj minus kvt, okay, and we define omega is equal to kv, okay, or omega is equal to so omega here is what we call frequency. Okay, so what you get here is at the end G minus omega t. Okay, so this is angular frequency, which is related to frequency by this formula. So you all know this, I know. I'm just writing it down so that everyone is on the same page. So yeah, this is simple, simple thing about wave. Please let me know if you have any confusion till here, or any thing that you want to ask. Everything is fine, right? Okay, now so the wave optics that we are going to study, as you can see here, wave, I mean, we have covered the wave part. Now there is this optics part. Okay, so optics means this light, right? And we know that the wave associated with light are electromagnetic waves, right? This was proved by Maxwell in the mid 19th century. So what Maxwell told us is that the light that we see around us are nothing but electromagnetic waves. So they are just like waves on a string, but waves of electric and magnetic fields. And they are governed by these Maxwell equations, which I will just write it down. So I am writing the Maxwell equation in vacuum. So this is the Faraday law. And okay, right, sorry, magnetic field. So these are the Maxwell's equation, and the solution to this Maxwell equation will look like something like this. Okay, sorry. Okay, I'm not mentioning the direction and all. I'm just writing this. So you see, this is exactly what we have written here for a wave on a string, right? I mean, so actually from this Maxwell got the clue that okay, so when he solved these equations, the solutions were just these these plane waves, and from here he got the clue that okay, so maybe the light is nothing but a electromagnetic wave. And also he measured the speed of this wave. I mean, from here you can measure the speed of the wave, and he got very close. I mean, the value he got was very close to what was the speed of light measured at that time. So these things led us to this discovery that okay, electromagnetic wave is nothing but light. Someone is unmuted, so can you mute yourself? There's noise coming. Okay, so this is fine. Now some quantities that we will be interested in this course. So as someone mentioned that waves carry energy, and one way to quantify that is to define something called Poynting vector, which is given by this quantity. Okay, So what is Poynting vector? So Poynting vector is basically the energy per unit area per unit energy per unit time passing through a finite area. Okay, so for example you can write it like this. So if you take dot product with some finite area dA, then this is just energy per unit time, okay, which is nothing but power. So this is, it's called energy flux density, okay, and it is a cross product of electric and magnetic fields. So this is how the waves carry energy in this form. Yeah, and as I mentioned, so these are called, plane waves. Why they are plane waves? Anyone know why we call them plane waves? Anyone can answer, please? No one? So okay, if no one wants to answer, I'll just constant phase surface form on a plane. I mean, uh, phase surface. What do you mean? No, it's not correct. So it's simple. Just you see the formula here. I mean, you just see the form of this function. So you see there is only z dependence here, right? There is no x or y dependence of this electric or magnetic field. So that means the wave is, so the field is basically uniform over, every plane. So if you have this wave passing out and you draw a plane here, so electric and magnetic field will be uniform on over this plane. Okay, the perpendicular planes that you draw. Okay, so that is what is referred to, because that is why these waves are referred to plane waves. Okay, if you have additional terms here beyond z direction, so if you have x or y dependence here, then they will no longer be plane waves. Okay, they will become then spherical or cylindrical or whatever weird kind of waves. So plane waves means fields are uniform over every plane perpendicular to the direction of propagation. Okay, so basically no in our convention of this axis, so no x and y dependence. Okay, so this is simply what we call plane waves. And then from these Maxwell equation there are various things that you can do, like if you have been given electric field of the electromagnetic wave, you can find the magnetic field using these Maxwell's equation. So these are very simple exercises from if you have done a bachelor course in physics, then you would have been expert in these kind of problems. So you can find magnetic field using this formula. Okay, where this k is the unit vector in the direction of this wave vector. Okay, so yeah, we will solve some problems where we'll apply this formula. Okay, Uh, so yeah, that's all that I wanted to recap. So anyone has any question till here, or anything that you want to ask? Otherwise, we can go on and solve some problems. I mean, apply these concepts to problems. If everyone is fine, then let's move to some examples. Okay, so first example uh, starts with the word example. So an example of coherent source of light. This one should be very easy. Anyone would like to answer?
Laser.
Okay, who was that? Uh, can you
I'm
explain
not.
why lasers?
Laser. Laser is all satisfy the coherent properties, nearly same amplitude and same frequency and constant phase difference with respect to time. That is the properties of coherence, and laser follow that.
Uh, yeah, I mean, yeah, phase difference, you're right, should be constant. So why they follow? Do you know why the light emitted by laser have constant phase difference and frequency is constant? Why this happens in a laser? Why not in a filament bulb or in LED or sun?
Because stimulated emission is there, and another spontaneous emission is there. Ordinary light related to spontaneous emission, and laser related to stimulated emission.
Yeah, I mean that is the full form of laser. But what do you mean by stimulated emission? Like,
In metastable state, atoms remains for longer time than
yeah,
they all emitted photons or
yeah,
energies.
yeah,
है
yeah,
ना?
yeah. That's right. So here the emission takes place from when there is a transition from metastable state to ground state, and these kind of uh, these kind of radiation uh, they, they are called stimulated emission, and they have fixed frequency and constant phase difference. So yeah, laser is a very good source of coherent light. So all the experiments are done in various labs. uh, they use this, I mean all the optical experiments, they all use this laser. Okay, so there are various types of laser, solid state laser, and very advanced lasers are there right nowadays. So yeah, that is a good answer, thank you. Okay, so this was an easy one. Then we can go to the next. Okay, so here is a bit involved problem. So here there is a wave equation, okay, wave function basically, uh, given by psi. I'll just write it out. So first of all, does this look like a wave equation to you, or is it not? Who thinks that this is not a wave equation? Everyone agree that this is a wave equation, right?
Yes, it is a wave equation because we can write it here in Euler form, e to the power I omega,
No.
that type of.
There is no I. It's just exponential.
Okay.
So yeah, then why this is a wave equation?
It can be rewritten in the form of x minus vt.
X minus,
Vt.
yeah. So you see there is a this is nothing, I mean there is a dependence of x and t that you can see here, and uh, I mean so simply it is nothing but you know so this is nothing but a, I mean under root x plus under root b t square, right? Right? So this is just a function, okay? And so it doesn't matter that you have to have a cos or sine dependence to get a wave, okay? Or e to the power I or something like that. So e to the power I is just, you are saying that it is just a complex form of cos and sine. So you don't need that. What you need is this form, okay? So it should shift in as time progresses. It should have a shifted value, okay? So it doesn't matter what function is it. It can be, you know, anything. Okay, and there are some other conditions that it need to satisfy in order to be a wave, but that I will discuss in a later problem. So there is a problem there in the later exercise. So yeah, but yeah, for now just you have to look at this dependence here. Okay, so but yeah, no, I would like to ask, so is it a shift in negative direction or positive direction? What do you think?
So negative direction.
Negative, yeah. So this wave will be propagating in a negative x direction, right?
Yes.
And what will be the speed?
It is omega by k. We can just
No,
shortcut.
yeah, omega. No, you don't need it. Just you have to get this form, right? X plus vt. So you can take under root a outside, then you will get this, right? So simply your speed is under root b by a, and move
Sir,
in negative direction.
in the same manner, sir, omega t minus kx omega by k. So also we will get under root b by under root a.
Yeah, but here there is no omega or k, right?
Let me assume that wave equation
That is fine. I'm just saying that. So yeah, I'm just keeping things general here. So, just you have to get this form, okay? Just this shifted form, x plus some constant t, and whatever that constant will be, that will be the velocity of your wave, okay? Whatever you call it, omega, k, however you interpret it, that doesn't matter. Okay, so fine. This one was easy. Then let's move to the next problem. Yeah, so this was the problem I was talking about. So now I just mentioned that whenever you have this form, some constant x plus some constant t, it should represent a wave, okay? So by that logic, all of these should represent waves, but it's not true. So why it's not true, and which one represent waves? So there can be more than one answer. So can you guys guess which one will represent a wave and which one will not?
I think C is correct.
C is correct. Why?
C is represent
Yeah, why?
because sine cos.
No, it's not cos.
Sine cos.
Sorry, it's cot. It's cot
It is
function.
what?
Now tell me, which one is correct? Any others can also get involved. So others are not speaking. So I encourage all of you guys to come forward and discuss. So it's nothing to get to get wrong. We are just starting, so you can just answer, right? Yeah. Anyone else want to guess?
The amplitude should be finite, so that would eliminate A and B, right?
Wait. Yeah. So yeah, that's a very good answer. So yeah, at infinity you have to check, right? So that there is no no singularity or shooting of the function. Yeah. So yeah, that removes these two. Fine. Then
But wouldn't that also remove the cot one?
Why cot? Cot doesn't go. Cot goes. Yeah. Cot goes infinity. Yeah. Yeah. So, yeah. Fine. Then what about this?
The denominator cannot be zero, so it is always finite.
Yeah. So, is it a wave? Does it represent a wave?
It does follow the x minus vt form.
Yeah, it does. But do you think it can represent a wave? Of course it can, right? Everything is there. It doesn't, it has no discontinuity, it has no singularity. You have the x plus vt form, so why not? Yeah, it is a wave. So yeah, D is correct. Others are wrong. Great.
Hello.
Yeah.
So in the assignment, the question is framed like which of the given mathematical expression satisfies the wave equation.
Okay.
So shouldn't all of them satisfy the wave equation?
I have not seen the assignment for this week, so uh, I can take a look. But if you have, how can you like? Yeah. So okay. So can you read the question? What it exactly says?
So the options are all same, but just the question states that which of the given mathematical expression satisfies the wave equation.
Yeah. Then you have to check this singularity thing also.
Okay.
Yeah.
Thank you.
Yeah. Yeah. Oh, so that was your question, right? In the beginning.
Yeah.
Okay. Is it fine now? Is it clear?
Yeah.
Yeah.
It
Okay.
is.
Thank you. So okay, then let's move to the next problem. Everyone is fine here, right? So like I was saying, so wave wave equation should be continuous, so there should not be any discontinuity, okay, and should not no singularity, okay, no singularity should be there. Then you will have, then obviously this kx plus x plus vt form should be there, plus these criteria should be there to satisfy a wave form, okay. Anyone has any question here? Thank you. Okay, so let's move to the next problem. So now it is a similar kind of problem. So which one of the following does not describe a traveling wave? Again, anyone want to take a guess? Sorry. Maybe option 1. Okay, option 1. We have one vote for option 1. Then this is easily a wave, right? Is this, what about this? You have g square, z square and t square. Can it be a wave? quadratic dependence. Anyone else want to take a guess? Option 4. Okay. Who was that? Ananya. Right. Yeah, you're right. So this one will not be, I mean, this is not a way, because you cannot reduce it to this form, right? Some function of this form. So yeah, this is right. So this is the correct option. Others you can do. So this one is fine. This one you can reduce it to this form, z minus vt to the power something. This one is also fine, right? This one is also fine. There's no problem. It's just a constant phase. C is just a constant phase, so it's okay, right? You have this wave. You just shifted it by a constant distance. That's all. You have a phase here. There's nothing wrong. Okay. Everyone agree?
Yes, sir.
Thank you. So yeah, then let's go to the next problem. Okay, now then you have these 4 options, and the questions asks which of the following expression represent a wave function of a harmonic wave of amplitude 10 to the power 3 volt per meter. Period is the time period, 2 into 10 to the power minus 15 seconds, and speed of light, which is 3 into 10 to the power 8 meter per second. The wave is propagating along the negative y direction, okay, and has a value of 10 to the power 3 volt per meter at t equal to 0 and y equal to 0. Okay, so this is the initial condition is given, right? Now as you can see, all of them have plus sign, so they all are moving in negative direction, so that is okay. That doesn't give us any clue. Okay, all of them have amplitude 10 to the power 3, that is also fine. But now how can we see which one is correct? So the you can look at the time period and the speed, right? So time period is 2 pi by omega, right? And from here you can calculate so basically these all wave functions are of the form a cos k y plus vt, right? And we know that omega is equal to kv, right? So if you multiply, so you can check, like you can calculate the omega for each one, and from here the time period is given, so you can also get the omega from here, and then you can check which one is the correct option, right? Everyone can do it, right? It's just simple algebra. Sorry, arithmetic. Should I do it, or you guys are fine?
So solve it, please.
Oh, I solved it? Okay, thank you. Okay, let's see. So first, let's calculate the omega, so which is 2 pi by t, right? So 6.28 divided by time period is 2 into 10 to the power minus 15 second. So omega you get is 3.14 into 10 to the power minus 15, right? So this is the omega. Now you multiply for all the options, okay. Sorry, 10 to the power 15, because this goes over, right? So for this, omega will be what? Omega will be 3, so 3.15 into 10 to the power 86, so it will be 14, I guess. Yeah, no, sorry, let me do it. So yeah, this will be 10 30 31.5 into 10 to the power 14, right? And so if you shift 1 point, 3.15 into 10 to the power 15. So yeah, I think A is correct, right? Yeah. Yeah, A is correct. Because see, why it is a cos, why not sine? Anyone want to answer? Why it would be a cos, not sine?
Maybe it starts from extreme position.
No, because you see the initial condition at t equal to 0 and y equal to 0, you have not 0 but the amplitude, which is 10 to the power 3. So this is like this, okay? So that's why the cos will satisfy, okay? All fine?
सर ये जो ओमेगा आपने निकाला, that is you multiply this 10.5 into this 3 into 10 to the power 8
Yeah,
by this relation kV,
yeah,
K into V.
yeah. So as I said, so
Okay.
here k is your 10.5 into 10 to the power 6 and v is your 3 into 10 to the power 8, right? So you
Okay.
multiply these together, you get omega, and then you can match the omega that you get from the time period calculation, right?
Okay.
Yeah.
Thank you, sir.
So okay, anyone has any other confusion? If not, let's move. Yeah, this one is very interesting. Now so far we have been talking about plane waves, right? Now I would like to mention other kind of waves through this problem. So you have to match these columns, okay? So there are 4 options: plane wave, spherical wave, cylindrical wave, harmonic wave, okay? So let's see who get it correct, all of 4. So can you write your answer in the chat? I'll give you some time. You can look at the options and analyze. If you're not able to read it, I will write it for you here. Okay, so someone has written option D. Okay, others? So option D, okay, option D, 1 vote for option D. Others? I'll give you guys some time so you can think about it. So meanwhile, I will just describe what a spherical wave or cylindrical wave means. So yeah, so basically plane wave I have already described. Now spherical wave is something. So take a plane wave, but now the electric field or the magnetic field, uh, it has it has a uniform dependence on a sphere, not a plane. Okay, so you so suppose there is a something emitting a wave, and you get these kind of wavelets. Okay, and electric and magnetic fields will be constant over a sphere instead of a plane. Okay, and the direction of propagation will be normal to this these concentric spheres. So this is something called a spherical wave. Similarly, you have cylindrical wave where so cylindrical wave, suppose a line element can produce a cylindrical wave, and you have these kind of uh, wave forms. I'm not good at drawing. Okay, so it is similar to spherical wave, but for a line element you will get these kind of cylindrical concentric cylindrical waves, and the direction of propagation will be normal to this cylindrical surface. Okay, and harmonic wave is basically a harmonic wave is something which has dependence on cos and sine. So this one is easy. So B is a harmonic wave. Okay, so because it has a sign dependence, we call it harmonic. I mean, it is also a plane wave, but yeah, I mean it is also a plane wave, but let's call it harmonic wave because there is no option here calling it a plane wave. So yeah, so anyone else want to try? No one? Okay, then okay. C Bhumika has okay. One vote comes for C. Okay, okay, fine. So yeah, mm, yeah, yeah. So Bhumika, you are right. C is the correct option. Sorry, whoever chose the D option, it's wrong. Ashish Tiwari, I guess. Yeah. So yeah, this is a plane wave. So I'll write here. So this is a plane wave. Okay, don't get fooled by this R here. You will see I mean you will think that okay, the R is here, so that means there will be X, Y and Z dependence, but that is not true, right? Because you see it is just an arbitrary direction. It is just the Z direction that we choose. It was just an arbitrary direction. You can choose any direction given by R. Okay, as long as it is since it is dotted with k vector, so propagation vector, so it is propagating in a in a direction that is r. Okay, and then you can simply choose your axis such that this direction correspond to z direction. So this is this can this is the same as kz minus omega t. So this is nothing but a plane wave. Okay, still satisfy the criteria for a plane wave, C option. And then if you have this uh, decaying of this plane wave, as it propagates as by 1 by r, okay, this is what we call a spherical wave. So now what will happen is that your electric field so suppose it will not be constant as the wave travels. It will have a reduced magnitude as it travels outward, so it will form a sphere. So and this 1 by r dependence is a very hallmark of this its decay. The 1 by r decay gives you basically a spherical concentric spherical surfaces over which the electric field will be constant. And similarly this under root r dependence of this kind of line element source, this will give you a cylindrical wave. So this will also decay as it moves radially outward. And harmonic wave, as I mentioned, so sine and cos are called harmonic waves. Okay, so yeah, this was a little bit tricky, but Bhumika is right. Anyone has any doubt? So you can try to visualize it. Maybe you can use some some software also, like Desmos or something, to plot it and visualize it. It's a nice exercise. Okay, so if everyone is fine with it, let's move to the next problem. So we have, I think, 2-3 more problems. Yeah, so this is a numerical. It's a good exercise. So okay, so now we go back to laser. So here a 500 watt laser is concentrated by a thin lens to a cross sectional area of 10 to the power minus 10 meters square. Okay, the value of the Poynting vector and the amplitude of the electric field is given by. So we have to find the Poynting vector, the value of the Poynting vector and amplitude of the electric field. Okay, now how to do it? The power of the laser is given 500 watt, and the area, the cross sectional area where the laser is being pointed is also given, and we have to find this and this. Okay, so anyone has any idea how to do it? So if you go back to the definition of Poynting vector, it is nothing but energy flux density. That is so if you take a area element, okay, this is just power, right? So this is the energy per unit time crossing through this area, right? From the definition I mentioned here, right? S dot d is just the energy per unit time, which is nothing but power. Okay, so from here we know the power of the laser is given 500 watt, Poynting vector magnitude, area is given. So Poynting vector magnitude will be simply 500 into 10 to the power 10, which is 5 into 10 to the power 12 watt per meter square. Okay, now this one is easy. Now how do you find the magnitude of the amplitude of the electric field? Anyone has any idea? So okay, let me try. So we know Poynting vector is nothing but 1 over mu naught E cross B, right? And we are interested only in the magnitude, only in the amplitude. E is just E naught, then you have cos something. B is B naught, then you have cos something, right? And we also know that magnetic field is given as this, right? So for amplitude the relation will be simply E naught by C, right? And so if you substitute that here, you will get E naught square, okay? So I'm just writing the amplitude. Mu naught is here and C. And there will be a 1 by 2 term coming because of this cos, because you have to multiply this cos terms, and that will give you a half factor here, okay? And this yeah, anything else will be coming here? No, I think yeah, I think this is the formula. So now you have everything, right? You know the magnitude of the Poynting vector, you know the speed of light, mu naught, you know, so you can calculate the amplitude of the electric field. Is it fine? The answer will be B, so you can give it a try. Is it okay? If everyone is okay, then I'll move to the next problem. This one was easy, right? Just you have to use these two formulas, so this and this. Okay, here is a similar problem, but don't get intimidated by the long expression. It's just just a vector form of the electric field. So here you can see explicitly the k propagation vector and the direction of the propagation, the amplitude is also has some specific direction. So electric field is not vibrating in a simple x or y axis but in some arbitrary direction. Okay. Yeah. So what we have to find here is the magnetic field associated with this electromagnetic wave whose electric field is given here. Okay. So we know the formula, right? We know this is the formula to use, right? Where this k is the unit vector of the propagation. Okay. So now let's see how we can solve it. First, what we can do is we can write out what are the information available here. Okay. So first we can see here that it has the form of a plane wave, right, where k dot r is your this quantity root 2 x plus y by 3 pi into 10 to the power 7. Fine. So I mean, just by looking here you can say that so your k vector would be something of the form 2 by 3 I cap plus 1 by 3 j cap, right? This much you can guess, right? And your r will be x I cap plus y I cap, pi and these things you can, right? If you take the dot product between these two, you will get this, right? But you have to find the unit vector here, right? So you will have to normalize it by the magnitude of this k vector. Okay. So the magnitude of k vector will be just x component squared, so under root 2 by 3 squared plus y component squared of the square root of the whole, and this will give you, so I am taking 1 by 3 outside, then 2 plus 1 will be here, so this will be under root 3 by 3, so this is 1 by root 3. So your unit vector will be k by the magnitude of the k vector, right, which is nothing but, so just I am dividing this by 1 by root 3. Okay, you will get this. So this is your unit propagation vector. Okay, so now we have this, and we already have given the electric field, so everything we can now calculate the magnetic field. Okay. Yeah, one more thing we have to do is we have to take the cross product, right? So as you see here, this electric field has this direction, so the electric field amplitude now is a vector in this direction, right? I minus under root 2j. So first we need to find the direction, or the amplitude of the magnetic field, which will be, which will have the same form right? This we have calculated here, and this is here, so we have to just take a cross product. Okay, so what is the cross product of K and E? So this is 1 by root 3, okay, yeah, by root 3 under root 2 I. So you can stop me if you are not following. I can repeat any step that you are not following. Okay, do not hesitate. And E naught vector is your I minus 2 under root 2j. Okay, so all of you know how to take a cross product, right? You can use this matrix thing I j. You can write the components here. Then the determinant of this matrix will basically give you the cross product here. Okay, so I think these things you guys know. So here 1 by under root 3 is constant, and what you will have here is, so this here is the this k here is the unit vector in the z direction. Okay, maybe I should write z to avoid confusion. Minus z, sorry, okay, minus under root 3, sorry. So this is the cross product finally, minus under root 3 in the z direction. Fine. Now we have everything. We can now we can simply write. So we have the amplitude of a magnetic field, which is simply now I have switched to this k here. Okay, and yeah, and you can see the magnetic I mean, from the options you can see the magnetic field is simply in the z direction under root 3 by c. So I think the option doesn't have the c, so I think yeah, you can replace it by 3 into 10 to the power 8, okay, into 10 to the power 4, and then you have the same form of exponential. This will remain the same, right? This will not change, only the amplitude direction will change. Okay, so which one matches? I think minus, so this will be minus k 1 by 3 10 to the power minus 4, right? Exponential of this. So I think it matches to B. Okay, so B is your correct answer. Everyone okay? Anyone has any doubt in this solution? So this is a bit involved problem, but it's nothing but simple vector calculations that you guys are familiar with. So what we did is we have this expression for magnetic field for a given electric field of an electromagnetic wave. Okay, first we identified here that what is the k dot r in the electric field. Then we separated k and r, okay, because we needed the unit vector in the direction of k. So we took the magnitude, we calculated the magnitude of the k vector here, which was 1 by under root 3. Then we calculated the unit vector by dividing the k vector by the magnitude, okay, which is this. And then we had the propagation direction, we have the amplitude of the electric field here in this direction, and we used this formula to calculate the amplitude of the magnetic field, okay, which was just to take the cross product of k unit vector in k and the electric field magnitude, okay, which we got minus square root 3 in the z direction, and we just put it here in this expression for magnetic field, because whatever is inside this exponential will not change, okay, whatever will change is the amplitude. Everyone is okay with this? So whenever you get this kind of problem, you don't need to worry about what is inside this function. What you have to worry about is what is the amplitude, okay. This just you have to calculate for the magnetic field given electric field, and it can be inverse of it, like you can in some problem you will get magnetic field and you have to calculate the electric field corresponding to that. So it's basically the same problem. So let's solve one problem such like that. Okay, so here you have this magnetic field given, and we have to calculate the Poynting vector. So you know that for Poynting vector you need electric field, right? Because this is the formula for Poynting vector, and as I mentioned earlier, so the amplitude of the electric field is nothing but in vacuum C times the amplitude of the magnetic field, right? So yeah, so one way to do it is yeah, I mean, so what we want is Poynting vector, which is nothing but the magnitude of the Poynting vector and the direction in which it is propagating. So as you can see, all the direction are z direction, which is which makes sense because your magnetic field is in your magnetic field is in pointing in it is a superposition of cos and sine, okay, and then you will have electric field which will be also a superposition of x and y direction, so somewhere in the middle of x and y, and so the Poynting vector will be perpendicular to E and B, which is only direction is the z direction, right? So we know that the direction of Poynting vector will be z, so what we have to calculate is just the magnitude of the Poynting vector, and which is nothing but just the magnitude of E and B, the amplitude of the E and B, and here I have the electric field is C times B, where C is the speed of light, and we can write it as omega by k, correct? Which is given in the problem, omega and k. So yeah, this is nothing, I mean, simply omega by k mu naught b naught square in z direction. Sorry, this is so this is a shortcut way to do it. Uh, so I mean, the important thing here is to know how to calculate the direction of the Poynting vector, because you see the magnetic field is in somewhere in the xy plane, and electric field will be perpendicular to the magnetic field, and Poynting vector we know is the perpendicular to both electric and magnetic field, right? And since this is a plane wave, so electric field will be lying on this xy plane, so the z axis will be the direction of the Poynting vector. Okay. So yeah, this is A is your correct option. Everyone okay? So I think, yeah, this was the last problem. So let me know if you have any question to ask. Many of you guys are not saying anything. I don't know if you are following or not, but I hope these are not, these are just starting points. If you have done bachelor courses in physics, these are the problems you have already accustomed to. So I hope this is not too tough. Or you can let me know if this is tough, or this is not aligning with the tutorial assignment that you are getting. Then I can try to adapt the problems according to your need. So yeah, feedback is very important. So let me know what you guys think. And so the timing of the live session is same. So 5 to 7 p.m. we have the window each Saturday. I mean, we can finish it earlier. It doesn't have to go to 2 hours. So like today we are almost done, unless you have any question or any doubt that you want to discuss, or any general item that you want to discuss. Everyone is fine? Okay, so if everything is fine, then let's close the session today, and I'll see you next Saturday. Thank you for joining. Bye.
Thank you, sir.